Okay, let's get ourselves underway. So welcome to day 2. Today we're going to finish this overview of the whole heliophysics system. And the question we're going to get down to not the ground, but basically close to the Earth. And I'm going to ask not only the Earth, but other planets, why it is the Earth has an ionosphere and a magnetosphere, and other planets, do they have ionospheres and or magnetospheres? And the logic here, you can see that today we're asking, why do the planets and the Earth have an ionosphere? And the answer, in short, is because of the sun's corona. Okay? The EUV and X-ray radiation from the corona is what creates the ionosphere. Then you ask, well, why does the sun have a corona? That was yesterday afternoon. I hope you all still remember. The answer was because it has a magnetic field. The magnetic field creates the heat, and then the attempt to get rid of the energy from that heating through radiation leads to a very hot corona and a transition region, which is where all of the EUV and X-ray radiation comes from. So the sun has a corona, we have an ionosphere. Why does the sun have a corona? Because it has a magnetic field. Why does the sun have a magnetic field? Because it has a dynamo. Okay, so these are all sort of linked. But we are now out of the realm of pure plasma physics and into the realm of dealing with a neutral atmosphere. This is the Earth's atmosphere. It's 77% nitrogen, N2, 21% oxygen, a little teeny bit of water, even less in Boulder, Colorado, and some carbon dioxide. And here is the temperature as a function of height. It's traditional, since things up is vertical, to plot the height axis this way, and then this is the y-axis, if you will. And you can see that for a good portion of the atmosphere, the temperature isn't that different from about 200 Kelvin. The sun, visible light, hits the ground, warms up the ground, and that heat is transported through the troposphere upward, down the temperature gradient from hot to cold. Then we get this weird region of the stratosphere where the temperature actually goes the other way, and then the mesosphere where it's basically in the direction to move heat upward again. So there's this stratopause where there's evidently, since there's a peak in temperature, some sort of heat source. So the atmosphere is being heated right there about 50 kilometers at the stratopause. And then again, we have this portion above 100 kilometers that is the thermosphere. There's obviously a heat source up there. So we have two regions where the neutral atmosphere is being heated. Why is that? Here is certainly one of the most useful plots we have from, for this exercise, and it comes from volume 3. And it is a plot. Now we have wavelength down here and height in the atmosphere here. And in the color code, I've colored it up, but basically yellow is a high amount of energy deposition from the sunlight. And it falls off to purple, and white is virtually 0. And you can see below a certain level, there's no energy deposition because sunlight of that wavelength doesn't reach below that height. Okay? And you can see there's this band of very strong heating around 200 to 300 nanometers. Quite strong, around 250 nanometers. I have to keep converting from angstroms, 2,500 angstroms. That energy deposition at 2,500 angstroms is, by and large, what creates the stratopause. That's the source of energy. Now, if we look at, this is the other plot that's going to be very important. This I showed you yesterday, although it was on a logarithmic wavelength axis. I've stretched it out so I could make it match up against this. The blue is the intensity of radiation, milliwatts per square meter per nanometer, from a given wavelength of sunlight. It goes like this. The red is the black body curve. And you remember for visible wavelengths, which are way over here and below, the solar radiation fits a black body curve very, very nicely. We suppress all these nice little Fraunhofer absorption lines. Right around 300, it starts to depart. At first, it's below the black body curve. And then we have this region here, which we talked extensively about yesterday. This is the extreme ultraviolet and X-ray radiation down here from the transition region in the corona. This is basically the stuff we're going to be talking about. It's much brighter than it would be if the sun was really just a black body at 5770. Okay? All that excess emission is coming from the corona, and it's all absorbed up there. I should point out my own personal bias is I like to observe the corona, and the sunlight is not making it below 100 kilometers below the, down beyond 100 kilometers from the surface. So if you want to make an image of the solar corona in these wavelengths, such as at 171 angstroms, the most beautiful wavelength to observe the corona in, you've got to get up. And we are currently waiting the launch, which has been postponed, of the High-C rocket, which is going up from White Sands, New Mexico. It was supposed to go up last week. Little fault with the payload, and they've delayed the launch. When it goes up, it'll get up to almost 300 kilometers, maybe 300 kilometers, and make the highest resolution images in 171 angstroms that we've ever seen. And the reason they have to go up on a rocket is they need to be up above where this light can be observed. Okay, so, but let's get back to what the ionosphere is. And we've sort of seen how this all works. What we need to do to understand this is figure out what happens to these photons, especially these very short wavelength photons, as they enter the atmosphere. And to do this, we just need to work out a probability that a photon will survive. And the probability depends on this thing called the optical path. If the photon has a cross-section for being absorbed by any absorber in the atmosphere, an average absorber, it has a cross-section sigma, centimeters squared. Then there's something called the optical path, which is the density of absorbers, centimeters to the minus 3, times sigma integrated over path length. That is what's known as the optical path. What it means, it's represented as tau. It's the average number of absorbers that's in a cylinder of that total length, right? How many absorbers there are. There's a very key point when you get to 1, so you have on average one thing that can absorb you along your path, you figure you're doomed, right? You're going to be absorbed. Is that right? If I have on average one absorber, one thing that's going to stop me, I will be stopped. True or false? On average, I have one thing that's going to stop me, on average, then I will be stopped, 100% probability of being stopped. True or false? You could ask this in a more quotidian way. You have one customer enters the store every 5 minutes. So you wait 5 minutes, exactly one customer will enter the store. True or false? False. What is the probability 0 customers enter the store in that 5-minute interval? 50%. That's a guess, right? Yeah. Does anyone know the kind of statistics we're talking about here? Sometimes they're called counting statistics. Poisson statistics. So the Poisson probability, if you have an average rate of an average expectation value of mu, then the probability of seeing 0 is e to the minus mu. So sorry, Charlie, you didn't pay your tuition. You can't ask questions. Oh. I don't want to say too much more. I'll get into it a bit later. Okay? It's just a cross-section, right? Absorption cross-section. E to the minus mu. So for 1, it's e to the minus 1. So we often talk in physics about an e-folding issue. Right? That is when you have one absorber, your probability of not being absorbed is e to the minus 1. If there's on average 2, it's e to the minus 2, etc. So you have e to the minus this path length. probability of surviving. Okay? Now, let's then think, we have this cross-section for being absorbed, and this is the path length. This is the all-important thing. Think about a photon coming from the sun down to a certain height, and what is my optical path length? Well, first of all, I'm not going to assume the sun is at the zenith, right? It's at some angle chi from the zenith coming down along this path. So first of all, the path length increases while the height decreases, so I get a minus sign. And then I just do a little bit of trigonometry, and I find that the path length is the height interval minus the height interval times the secant of this angle. Okay, so if I'm at zenith, secant of 0 is 1. Secant is 1 over cosine, so it's 1. So my height is basically the same as my path length, but just backwards. As the sun gets lower, the path length actually gets to be a larger multiple of the height. And as it goes to sunset, well, we're talking about a planar atmosphere. This isn't a spherical Earth. So actually, it goes to infinity. Secant of pi over 2 is infinity. So it would never actually reach me. Anyway, that's the simple calculus. The other thing I'm going to assume, and this is very crude, but it helps us get some math done, and that is that the density, the number of scatterers, is falling off exponentially with height. It has some density at the ground, and then it falls off exponentially with another very important number called the scale height. This is the pressure scale height or the density scale height. And so the number density scales exponentially with height. When I do this integral, I get a path length that is this absorption cross-section, the number density at the ground, h, and then my secant, and then my exponential. I can clean this up a lot if I basically define this to be something else. In other words, I take the logarithm of this and call that a height z tau 1. I believe it's called something else in the literature, but I like the fact that this reminds me, this is the height at which tau is equal to 1. And it's basically the scale height and then the logarithm of all this stuff in here. And when I do that, I basically have this function here. The path length is an exponential decreasing with height. So as I go to, if I go to very, very high heights, the path length is, the optical path is 0. Essentially, I have 0 scatterers if I get to infinity. If I'm on the ground, I have some other path length. Okay? Now here is the cool part, in my opinion. That makes the probability of surviving to a given depth, z, a given altitude, an exponential of an exponential. I've never in my years seen a function except in this one application. We get an exponential of an exponential. Okay? That is the probability of surviving down to that height. And we are out of batteries here, so we're on manual. So if I plot this, I basically can plot what is this e to the z tau over h. That's basically the cross-section. And what I find out is that's really the actual scattering cross-section that I have, that I observe, divided by some factor that involves only the mean mass of my scatterers, the gravity of Earth, the pressure at the ground, things we know. Okay? And I can just plug in all the numbers, and I get 5 times 10 to the minus 26 centimeters squared. It reminds you that atoms are very small. Okay? This is basically the area under one atom in the atmosphere. If I go all the way up with this cross-section, I will have one atom in my atmosphere. And if my scattering cross-section is bigger than that, my absorption cross-section is bigger than that, then my tau equals 1 surface must be higher up than the ground. If it's smaller, then tau equals 1 would be below my feet. That doesn't really mean anything, okay? But that's just basically it. And here is that plot of that exponential of an exponential in blue, and the red is showing me where the tau equals 1 surface is when my cross-section is 10 to the minus 17. This is actually a pretty typical number. This is typical of a different wavelength, typical of yet another wavelength. You can see for this, you would think, wow, this is, what is that, 7 orders of magnitude larger than this canonical cross-section. But because it appears in a logarithm, that just basically puts the scattering cross-section up there. As I increase, the scattering cross-section comes, or as I decrease scattering cross-section, then the height of tau equals 1 moves downward. So far, so good? All right. Now, Charlie asked me to talk about this cross-section. And I don't want to go through all the details of how atoms absorb light. I will just say, here is a plot in units of centimeters squared of what this is as a function of wavelength. This is vastly simplified, but it's basically saying you have air, you have photons of this wavelength, say 50 nanometers, 500 angstroms. It has a very large cross-section for being absorbed. And as the wavelength decreases, there's some nutty stuff going on here. That's a lot of interesting details, but we can't really talk about them. And then the scattering cross-section falls off as the wavelength falls off. Increases, sorry. So that scattering cross-section is basically the logarithm of that gives me that height, the height at which I'm going to E-fold, where my probability of surviving is 1 over E. Okay? And I basically can take that same plot and plot it as the Z tau 1. And here it is. And here you have, this is from a lecture, but I think there's something like it in the book. This shows you the kinds of physics that's going on to absorb these photons. For this 2,500 angstrom absorption, what we really are looking at is mostly ozone is absorbing photons, 2,500 angstrom photons. This is why ozone is considered important for, for dropping down the ultraviolet light. It's actually keeping the light from penetrating below 50 kilometers. Okay, so as long as you're below 50 kilometers, you will encounter a lot less 2,500 angstrom photons. We also have absorption by oxygen molecules, nitrogen, oxygen, and all-important photoionization. That is, the photon that's being absorbed is being absorbed because it's knocking an electron out of the molecule. Now, the only molecule I understand, the only atom I understand, is hydrogen. Okay? Does anyone remember how much energy in electron volts it takes you to knock the electron out of the ground state for a hydrogen atom? 13 electron volts, yes. Does anyone remember the wavelength associated with that, a photon with 13 electron volts? The classic, certainly for astronomers, it's a well-known wavelength. (912 angstroms, 91, right? That's called the Lyman continuum. Okay, 1216 is even more famous. That just knocks it from the ground state up to n equals 1, n equals 2. Sorry. So 900 nanometers, that's where hydrogen would be. It's not on here because there isn't much hydrogen in the atmosphere. But suffice it to say, from a standpoint of an astronomer, atoms and molecules are atoms and molecules, right? So you get sort of tens of eV. I believe for oxygen it's like 12 eV to ionize it. For nitrogen it might be more like 15 eV electron volts. So it's all in that ballpark, and it's around this wavelength that you're being absorbed because you're knocking electrons out of the molecules. This is all important for the ionosphere. In fact, it's these shorter wavelength photons that are really doing it because they're knocking out the electron and then giving the electron some energy so it can get away. Right? You don't just want to pull it out. You want to pull it out and throw it away. So there you have it. This is the height of tau equals 1, where the photons are going to be absorbed. And if we know the probability of a photon making it, then we can sort of see, okay, this is why this plot looks this way. Essentially, this curve here is mirroring the cross-section for absorption. Right? So the reason that the EUV photons are absorbed so high up in the atmosphere is they have such a high cross-section for being absorbed. And then we have this bump here that comes from all of this oxygen absorption. And then this bump here, which is actually giving rise to our stratopause, is absorption from that bump in ozone. Now, the energy flux is basically the number of photons I started with times the probability that they've made it to a certain height. So this is the flux from the sun reaching 1 AU, and this is the flux down to the height z here, because it's weighted with the probability. If I take the derivative of that flux, I have how much energy didn't make it. This is the energy deposition, right? And now I have to take a derivative of this really cool function. The exponential of the exponential, it brings out another exponential, and I have this very interesting function that is an exponential of an exponential and a linear function. Even better. This kind of function is commonly referred to as the Chapman layer, and I've plotted it here in red. Here is the probability, but it's on a logarithmic scale, and you can see on a logarithmic scale even, the exponential of an exponential is very sharp. It falls off very rapidly here. So the energy deposition has this floor on it, and it has this tail. Now this is an exponential decrease, so on a linear scale you'd hardly be able to see any difference. But this is, at least logarithmically, this is more gradual fall off than the bottom. This is where the energy is being deposited, and you can sort of see that structure here. This is also a logarithmic scale. This is log, I cut off here, yeah, log 10 of the absorption, and so we have that hard floor and basically this exponential fall off, which is linear in the logarithmic scale. Oh, that's confusing. So here is my I infinity, 300 milliwatts per square meter, right here, and basically that turns into this level of energy deposition. It all just works out this way. That then tells me why we have so much energy being deposited here. It's because there's so much more light in this region here. So even if the sun didn't have a magnetosphere, look, if the sun didn't have a magnetic field, didn't have a corona, this is black body, so we would still have this ozone layer. But this region here is really coming from the corona, right? So this energy deposition is coming from the corona. And it's that's doing the photoionization. So from this wavelength range here, basically 100 kilometers and up, and 100 nanometers and shortward, we are getting ionization. And here's sort of a chemistry picture which shows you the different kinds of ionization we get. We can ionize an N2 molecule, and that will create some N molecules. We can ionize a pure oxygen atom, and we'll get a positive oxygen ion, oxygen molecule, etc. All of these ionizations are going on in this little region here. And basically, it means that in this region of the atmosphere where that ionization is happening, we are creating electrons and positive ions in pairs as we photoionize them. And lo and behold, that is where, if I plot the electron density, and this is in electrons per cubic meter, and of course, here they're assuming you realize that every time you create an electron, you're creating a positive ion. So there's exactly as many positive ions as there are electrons. They're just going to plot the electrons. And we see nothing below sort of 70 kilometers because none of the photons at that short wavelength that can photoionize make it below that altitude. So you just don't see any free electrons there. And then all the free electrons are in this layer here. This is the ionosphere. Okay? And all these photons are coming from the transition region in the corona. Very important. So we talked yesterday about why there even is a corona, and therefore there's a transition region. That's what gives rise to all these wavelengths. That's what gives rise to the photoionization and the ionosphere. So far, so good? Yeah. Yeah. Yes, I glossed over a whole topic called radiative transfer. So you can actually basically are you talking about the fact you can photoionize something and then you can have another recombination that emits another photon, or you can scatter that photon and you'll make it down. Yeah, this is a very hairy subject. I tried to make the simplest argument possible, saying that once a photon is absorbed, it disappears. But you can recombine and then re-emit that photon, which is essentially the same as if the photon came in and was scattered. And if it's scattered, it's not going along the same path, but it could make it further down. Actually, it's going to go off in all directions. Yes, it becomes very complicated. Does that answer your question? Yeah. Yeah. Okay. Tim, can you answer that? Negative ions. Why the heck do we have negative ions? Wow, okay. Thank you. If he can't answer it, then what chance do I have? Sorry, but it's an interesting question. This doesn't fit into my very simplistic view of what's going on. All right, so here is the way we explain the density of what these things are. That is, we have electrons and ions being created by photoionization. And the rate of production is proportional to this flux that we already worked out. The density of scatterers, which I'm assuming here is an exponential just to make my math easier, and a cross-section that really has to do with the total cross-section for ionization over all wavelengths and just the ionization part, not absorption by any other mechanism. So it's slightly different than the other sigma I was using, but suffice it to say we get the same Chapman layer profile. There's no z tau 1 here, but I could basically add it and subtract it off in the prefactor. We get the same production rate for electrons as we saw for energy absorption. It has that same structure, and here it's called Q. This is the number of electrons produced per time per volume, okay? And you'll notice it depends on the number of things that I can ionize. Here, I am tacitly assuming, I'm tacitly assuming this is the same as if there was no ionization going on at all. So in other words, I'm ignoring the fact that I've already ionized some fraction of them, and those aren't available to ionize again, not at that wavelength anyway. We'll see that that's a fine assumption to make. But then that basically would say that I just keep ionizing continuously, and I would eventually run out of neutral atoms, except for something they call electron destruction, but it's really those electrons can recombine with the positive ions and form neutral atoms again. So basically we have production and we have destruction. Okay, now this is actually rather complicated. If you go into the physics of combining a positive ion with an electron, it turns out it's very difficult to do and conserve both energy and momentum. So there's a lot of chemistry or complicated physics that goes on here. I'm going to ignore it and just say, well, whatever happens, you can describe with a coefficient alpha, but it does depend on the product of the density of electrons and the density of ions. And this actually appeared yesterday when I was trying to argue how much radiation occurred. I didn't draw attention to it. It basically has to do with how many collisions there are. You can only produce this neutral atom if an ion collides with a positive, with an electron. And so the rate is going to be proportional to the square of their densities. Sorry, the product of their densities. So that's why in a lot of these scattering problems, we do get these densities products. Or if I assume that there's the same number of positive ions as electrons, because actually they had to be created in pairs, then the loss rate is proportional to the density squared. This is basically the same reason that we have brightness in X-rays that's proportional to the density squared. It's proportional to the rate at which things are colliding, and that's this. Now, if we have an equilibrium, then the energy, the rate of production is balanced by the rate of destruction. The two balance each other out. So I can set this equal to that, and I can solve for the density of electrons. It's going to have to do with this density of production divided by this coefficient that contains a lot of physics I didn't want to discuss. Both are functions of height. This has that really cool profile, so you expect the electron density to have the square root of this cool profile, which on a logarithmic axis means half of this square profile. I didn't give you any axes here, so you don't even know what half would be. And lo and behold, that is what happens in equilibrium. As long as we're producing electrons, they are being destroyed at the same rate, and basically they reach equilibrium. Now, we don't always have equilibrium. First of all, half of the time, the sun is not shining, and we are not producing any more electrons. But that doesn't mean they all go away, because actually what happens is then you just have to go through loss with no production, and they will decay away. This goes as the density squared, so their rate of decay depends on how many there are. So as they decay, they will start decaying more slowly and more slowly. Suffice it to say, this is what happens. We basically have an equilibrium during the time when the sun is up. Right? We have this peak in the electron density, and here I'm plotting electron density, and this is in a linear color scale, and this is over the Millstone Hill radar in Massachusetts. This is a model. But basically, here's where the sun is on, and it's photoionizing, and then the electrons and ions are recombining, and you get an equilibrium. And then the sun goes down, and we stop the source. And what you see is low down, the minute you shut this source off, the electron density goes right down, it starts to recombine. Actually, very low down, as the sun gets lower in the sky, it's not even reaching these heights because of that secant. So it shuts off even earlier. And then up here, it takes quite a while for the electrons to recombine back down. On a logarithmic axis, it doesn't go away at all, but it does drop by here. It looks like 3 orders of magnitude. That's a big shutdown. On a linear scale, it looks like 0 here. Okay? So basically, as you might expect after this story, the ionosphere gets a lot less dense in the nighttime when there's no photoionization going on, and you're basically there because it's still taking you a time for the electrons to meet up with the appropriate ion and recombine. Okay, so there is this day-night variation. And the other thing to see is as you go up higher, the densities of everything are intrinsically smaller, and so it's taking longer and longer to decay away. So here is a picture in equilibrium of what's going on. And this is a very complicated graph, but what we have is the black curve is the electron density in centimeters to the minus 3. Here is that region. It doesn't even start. This is 100 kilometers. It doesn't show anything below that because there's virtually nothing to show. The dashed lines here are the neutral species. So you'll see nitrogen falling off. You'll see oxygen falling off. You can barely see in this light, there's a cyan line that is atomic oxygen falling off. And then there's helium in the atmosphere. Even though it was discovered in the sun, it does exist in the atmosphere. And it's falling off very, very gradually. Here are the ionized versions of those. So here's the ionized oxygen, right? Oxygen atoms. Matching the electron density, which is telling you that mostly what's being ionized here are atomic oxygen. It has a lower ionization threshold, so there's easier to do the ionization there. That's what's producing most of the electron-ion pairs. There's also some molecular oxygen being ionized, etc. A key point. Look at this. This is 10 to the 6, good number density for electrons. The number of atomic oxygen atoms to compare it to, and actually those are the dominant ones here, 1,000 times higher. So something to always keep in mind, when you're talking about the ionosphere, you're talking about the electron-ion pairs. They're only 0.1% of the things out there. The ionosphere is 99% neutral at its sort of peak area, and this is just a rough number, right? We just saw that it all varies. So this electron density falls off at night, but it's almost all neutrals. Nick? Yeah, I'm sorry. You can blame Stan Solomon, I believe, for this. I should have. Yeah, okay. So it's sort of a background question. Why do these things fall off at different rates? I will say this. They are all roughly at the same temperature. But the number of nitrogen molecules per cubic centimeter is getting smaller, faster than the number of atomic oxygen molecules. Why does that happen? Mass? What does mass have to do with it then? The scale height, yes. Do you know that formula for the scale height? mj, it's kT over mg. What you quoted was the much more useful inverse scale height, which is what you have to multiply. Yeah. So as the temperature goes up, the scale height goes up. These basically all fit. And so, sorry, I should have put it in here. Even more importantly, it's e to the minus z over h. So the scale height is telling us how fast this thing is falling off in an exponential. And so when I have a mass of 28 protons, like a nitrogen molecule, it falls off with a scale height of 43 kilometers. Oxygen, 38 kilometers. They sound similar, but you put them in the exponent, and the oxygen molecules are falling off way faster. And I, of course, made the same crazy color scheme choice here. Atomic oxygen, 76 kilometers for a scale height. So it's falling off much more slowly. I mean, that's a factor of 2 different, obviously, than the molecular oxygen. But in the exponent, that means by the time you get up here, atomic oxygen is dominating. And except until you get the helium dominating, which falls off with an amazing scale height of 300 kilometers. All right, so just to summarize where we've gotten to so far, the ions and electrons, they form a plasma. So a lot of the things we know about plasmas will apply to them. There are overwhelmingly more neutral atoms, okay? And these you can think of as an entirely separate fluid. However, these 2 fluids are very strongly coupled. Probably for no reason more important than the fact that they're constantly changing roles, right? Neutral atoms are becoming ions, ions are becoming neutral atoms, and so whenever you have that kind of exchange, it basically introduces an extremely strong coupling. So it creates a drag force. So ionospheric physicists talk about these fluids as separate fluids, but with a very strong drag force coupling them. The reason the ions and electrons as a separate fluid are so important is they are basically the things that respond to electric fields. One of the things they will do is they'll act as a conductor, and they will screen out any electric field that oscillates more slowly than the plasma frequency. And I've worked out, here's the plasma frequency, not the angular frequency, which we're used to seeing. This is the linear frequency. It's basically 10 kilohertz times the square root of the number density in inverse cubic centimeters. This has profound consequences for radio astronomy. As a solar physicist, I would love to see the solar corona at a lot of different frequencies. So my question, what is the lowest frequency I can hope to observe the solar corona at? What? 10 megahertz, right? The radio astronomer. First of all, I'm at a disadvantage this way because I'm looking at the sun, which is creating the ionosphere. If I were a nighttime astronomer, God forbid, I could do this at night, and the ionosphere would have a lower density. But if the density is 10 to the 6, I take the square root, I get 10 to the 3 here, 10 megahertz. You'll see plots sometimes that have radio data, and they go across that band. everything at frequencies lower than about 10 megahertz has to come from a spacecraft. So you pay dearly for every bit of data in that lower frequency wavelength. The stuff above that just comes from a radio dish on the ground. Not cheap, but doesn't cost what it costs to put stuff into space. All right, so now we're at the point where we start to see how the ionosphere responds to the corona. I showed this plot yesterday. This is the X-ray flux. This is 1 to 8 angstroms. Much shorter wavelengths than are creating the ionosphere, but it varies by a factor of 50 from solar min to solar max. We saw that yesterday. That comes about because the corona itself gets much more dense during the solar maximum, and we talked about that. So that means there are ionospheres that are created by a lot of EUV and X-ray flux from the corona at solar maximum, and then there's a profile that describes what it looks like at solar minimum. So the ionosphere actually has profiles that differ between, obviously between night and day, but also between solar max and solar min. Okay. Very important thing there. Remember, this is the density. Let me also pose the following simple thought question. I showed you one plot where I showed that this number here goes up by another factor of 100 during a solar flare. X-ray flux in this wavelength can go up to a factor of 100 even more, brighter temporarily. The photoionization band is not going up by that much, but it will go up by, let's just, for good numbers, put in a factor of 10. Let's say the ionizing radiation is increased by a factor of 10 just for a few minutes. But what will that do to the production, what will that do to the density, equilibrium density of electrons in the ionosphere when we see a flare like that? Energy flux, or photon flux goes up by a factor of 10. Electron density goes up by equilibrium. Actually, very complicated physics that goes into all this, but by 100? Yeah, 100? Everyone happy with 100? 3? 100 is 10 squared. 3 is square root of 10, as anyone would know. Yeah, it's actually the square root of that production, the flux. It's the square root of the flux. So it goes up by a factor of 3. That's pretty good, right? So this is something we're going to come back to. I think Tim will probably talk about, well, maybe not. But some people will talk about the way the ionosphere responds to just the solar flare itself, just the X-ray flux. And this is basically another plot due to Jan Soika that shows different levels of solar radiation and what the ionosphere looks like as the, and this is a characterization basically of the amount of X-ray flux. Okay, so it basically moves the ionosphere up a bit, but definitely increases the number density up by that much. All right, so that's the ionosphere on Earth. How about some other planets? Well, we have Earth with our nitrogen atmosphere. We have Venus and Mars actually have very similar atmospheres, if you just look at this, mostly CO2. So that's going to be a big difference there. The atmospheres themselves, the temperature at the base of Venus is very high, as we all know, but it falls off. They both lack this turnover here, which, as I saw, was caused by ozone, and they don't have any oxygen. So my assumption, not that I do this for a living, is that without the oxygen, they just don't have this feature in their atmosphere. It just falls straight off, and then we form the thermospheres up here. This is what the ionosphere looks like, and here we've plotted each of the species, but basically the electron density would just follow this outer profile. And in Venus, we get a density that's not too different from the Earth's, sort of up around just shy of 10 to the 6, at a roughly similar altitude as well. And this is all caused by the This is mostly caused by the photo dissociation that results from CO2 being ionized and creating oxygen, etc. So up there, we get that ionosphere. Mars, very similar diagram here because it's a very similar chemical composition. It's a little further from the sun. The densities are lower, so its ionospheric density is lower. But both of those planets have neutral atmospheres that create ionospheres. I'm not going to go into the ionospheres of the giant planets because I want to move on to discussing what happens when the solar wind, which we talked about yesterday at length, comes in contact with Mars or Venus. Simple cases because they don't have magnetic fields, but they do have this ionosphere. It's an electrically conducting layer. In fact, as long as the solar wind isn't varying on microsecond timescales, it looks like a perfect conductor. So we have a conducting sphere in the middle of the solar wind. Now, the solar wind material doesn't really care about the conductivity. Actually, the particles collide so infrequently, it's unclear it would care that much about Mars or Venus. The magnetic field, on the other hand, is holding on to those particles. It cares. It knows about Faraday's law. It knows that it can't penetrate into a conductor in a short period of time. So as far as the magnetic field goes, and therefore as far as the whole solar wind goes, it sees a spherical obstacle. It sees this ball that's impenetrable and it has to go around it. The other thing we saw is by the time you get out to 6, 10 solar radii, the solar wind is going supersonic. So it is an obstacle in a supersonic flow. Okay? Supersonic flows are really cool. As they encounter something, the wind has no way of knowing that. Okay? It has no information coming from downstream. So it just gets totally surprised by this spherical object. Well, what happens is we form a shock. Shock is, I heard it once beautifully described, shock in hydrodynamics is a hydrodynamic surprise. It is something where the fluid upstream has no way of knowing what's going to happen, and the shock is saying, hey, wait, there's something downstream we've got to go around, because it's a perfect obstacle. And so in this flow here, it's actually subsonic. And it's subsonic for two reasons, but one main reason. The first reason, which is sort of not that important, is the flow slows down a bit at the shock. Okay? But actually, if it's going 8 times the sound speed, it can't slow down by more than a factor of 4. So doesn't that make it going twice the sound speed after it slows down? So it's still supersonic and wouldn't know what's ahead of it? Why is that not right? What? Temperature goes up. Temperature goes up a lot, which means the sound speed goes up. So its velocity's gone down, but the sound speed's gone way up. It's very subsonic over here. That's a recipe for saying, hey, let's go around this thing. So we get this subsonic flow, which is the sheath flow, behind a bow shock. Very simple problem. In fact, you can work out the solution with a bunch of assumptions analytically and figure out how wide this layer is. Okay? What you assume is the inflow is just a really big Mach number. I don't even have to give you a number. It's just much, much greater than 1. It has some density that is, well, prescribed by the solar wind. When it hits the shock, it is a high Mach number shock, so the density increases by a factor of 4, the flow velocity decreases by a factor of 4, or the normal component of the flow velocity decreases by a factor of 4. The Mach number becomes very, very low. When you're at very, very low Mach numbers, no matter what material you have, your flow is incompressible. Okay? That's sort of why we have incompressible flow. It's not because you have fluids that are incompressible. That's one of my pet peeves. People who think there are incompressible fluids and therefore incompressible flow only applies to them. Incompressible flow applies to the air. Right? I was saying yesterday, all airplanes before World War II were designed using incompressible fluid dynamics because they never flew faster than the speed of sound. Everything was subsonic. Everything's incompressible. So if we have an incompressible flow, I can express it in terms of a stream function I turned out to have stolen this stream function, which gives me the behavior I need from Lightman, a very smart individual. And if I use this, I can figure out what the radial velocity is and what the tangential velocity is. The radial velocity going inward at the shock, tangential velocity. I have to match the conditions that basically the radial velocity decreases by a factor of 4. Oh, this shouldn't be minus. Yes, it should. By a factor of 4, so it's a quarter the upstream radial velocity, and the radial and the tangential velocity has to be the same. Yeah. Oh, sorry. Rankine-Hugoniot conditions. The Rankine-Hugoniot conditions are a very complex set of equations that come from some complicated relationships that conserve mass, momentum, and energy for a gas being shocked. And if our gas is a monatomic plasma, then it turns out that the asymptotic level of density compression, that the most you can compress by, is 4. If you have a neutral gas, sorry, it's not neutral, it's a diatomic gas, turns out it's 6. So I'm afraid we don't have time. Merev Ofer will talk about shocks. But just take it from me that your maximum compression ratio you can get from a shock is 4. And that is what we're assuming here. And so if the density goes up by a factor of 4, and you conserve mass, then your flow speed goes down by a factor of 4. When you're driving in traffic, it usually works the other way. If all the cars slow down, then the density of cars goes up, assuming no cars are being lost anywhere. You just basically have to conserve cars. You have to conserve mass. So your velocity goes down by a factor of 4. Your the density goes up by a factor of 4, but only in the normal direction. Okay, you match those. You basically get the following. This distance here, which appears inside this thing to the 5th power, has to be the 2/5 ratio of 3/2. Has to basically be, sorry, this, yes, this is right. 18% bigger than this. So the thickness of the sheath in this simple calculation is just set by a fixed number. As long as the Mach number is really, really big here and the Mach number is really, really small here, we get a simple layer like this. When we did numerical simulations, and this was done by Spreiter in the 60s, it's these black curves. So these black curves here, you see over here, in this region here, where we really trust them, this isn't such a bad approximation. And in fact, our estimate of how thick this is very close to the one you really get. A more important, or another consideration here, is what happens to the temperature. Now, as John pointed out, when the flow slows down, its temperature goes up. What has happened is you've taken the mean kinetic energy, the kinetic energy of the center of mass, 1/2 m u infinity squared, and converted a fraction of that. The fraction is 3/8. Again, this comes from Rankine-Hugoniot conditions, to heat. That's why your temperature goes up. Your kinetic energy of motion is converted partly to heat. The rest of it continues on in kinetic energy of motion because you haven't stopped. You've only decreased by a factor of 4, as well as the fact that you had to do work to compress, et cetera. You get 3/8. That is the stuff going here. If I look at a 400 kilometer per second wind, that temperature should be 3 megakelvin. That doesn't depend on the initial temperature, right? This just depends on the velocity. This is assuming that the initial temperature was maybe 0. It's not 0, but it's a lot lower than 3 megakelvin. So you shock and you heat up to 3 megakelvin. Then you slow down, convert some of the remaining kinetic energy to heat, and you get up to 16/15 of that. This is a lot of fun use of Bernoulli's principle. And the pressure ends up going up like that. So you have very high pressure here that is basically the ram pressure of the upstream flow. But the flow here is stationary. The flow here is stopped right at the nose. So it is in this sheath that we convert a lot of the upstream flow energy to heat, to temperature. We saw in the overall plot of the heliosphere that we had a source of heat right here. That's part of it. It's this shock that is converting the bulk kinetic energy of the solar wind into heat at the shock. Okay. Here's a little picture of someone's cartoon of what this looks like around Mars. There's the bow shock. There's a bunch of stuff from the ionosphere, all kinds of cool stuff going on in the ionosphere. This is basically the sheath region we were talking about here. Just want to focus on that, or just mention that part. This part I haven't even come close to explaining. Very similar picture for Venus. We have the bow shock. We have the sheath. And of course, downstream, none of that analysis we did applies, but there's that region that we worked out the detailed structure for. Let's see. I think we should take our 5-minute break before we move into magnetospheres. So let's just give ourselves a little pause and try to get ready to think about the magnetosphere. Start up again in 5 minutes. Yeah. Oh, okay. Good. We're here. Hey, good to see you. It's embarrassing to have to present this with you here, but yeah, it's very crude. So this is maybe a question. The ionosphere becoming collisionless. So I think the ion-neutral collision rate is always going to be pretty high because you always have to basically be producing one from the other.
Yeah, I mean the ions at about the ions at about 300 kilometers. They usually collide about once every 60. So there is still ion-neutral coupling even up to throughput. Eventually, but even the ions won't be collisionless even when you get out to the magnetosphere. Because the Coulomb interaction.
Yes.
So it still behaves like a collisional Coulomb attraction between plasma is still like so it's still collisional, although it's not the individual one. But when it gets down to the scale about 400 or 500 kilometers.
Yeah.
Was that your question?
There is this sort of exosphere, but that's, in my understanding, people are mostly talking about neutrals being collisionless. And neutrals can be very collisionless because they don't, there's hardly any ionized material for them to care about. The ions and electrons are like, we came from the neutrals, so how can we ignore the neutrals? We're constantly exchanging. Hydrostatic equilibrium does not involve collisions. Pressure does not involve collisions. This is a big misunderstanding. Yeah.
No, the reason I'm asking is I work on Python's ionosphere a bit.
Right.
Oh.
Scale heights of ions in the ionosphere, and they don't look like they're hydrostatic equilibrium at all. So when I saw your plot,
Hydrostatic equilibrium, then, to depart from that, I will say this just from a plasma physics standpoint. The key issue there is probably flows. Supersonic flows. The minute you have supersonic flows, now the pressure forces aren't going to be that important.
Yeah, I mean the fluid approximations for the Earth's atmosphere they're okay up to about 600 kilometers. So yeah, I need to work out that. It's when the mean free path scale height is sort of 40 or 50 kilometers. So when the mean free path gets so long, then the collisions are so infrequent, and they're just free particles. So for the Earth, that boundary is about 500-600 kilometers. I mean, it depends on the temperature. It stands in facts. So you can apply the hydrostatic balance up to that altitude.
I would argue you could have, Yeah, I'm still live, but that's okay. You could probably, I mean, if you have a completely collisionless collection of Maxwellian distribution of particles, it will have a equilibrium. It will have an exponential scale height. Regardless, no collisions required. Now, how would it become a Maxwellian distribution? That's collisions. So above 600 kilometers, you're going to start to say, oh, maybe this isn't really Maxwellian, and therefore, maybe I really can't even tell you what the scale height would be. Something makes it Maxwellian. Even you can. I don't know what you really do have, but I'm just saying from a basic plasma physics standpoint, if you take non-interacting particles, put them in a Maxwellian distribution at one height, it will be a Maxwellian distribution at all heights, and the density will fall off with the scale height.
Okay.
Now the temperature will be the same everywhere because they have no way of exchanging any temperature.
Okay.
So you get isothermal atmospheres from zero collisions, provided you have an isotropic distribution. that's begging the Titan's atmosphere. You're saying. The gravitational scale height. Yeah. Ooh. How ionized is that? Is it like this? Is it just very weakly ionized? Is it mostly neutrals? Yeah. Nor did I. Yeah, no, I didn't know that. Okay. Yeah, it's actually fascinating because when you go into the details of when you expect this hydrostatic balance, really doesn't rely on a lot of things, but there are a few things that can go wrong. The ones that I know most often in the solar convection zone are flows. Once you have supersonic flows, now the pressure is not a significant player. It's the inertia of the flow that's the significant player. That can have a big effect on it. Otherwise, through the whole convection zone of the star, it's hydrostatic.
You were saying that.
Yes, thanks.
Hydrostatic balance, you're saying, doesn't.
It does not depend on collisions. Yeah.
And that's based on.
It's just based on kinetic theory. You look at kinetic theory, because pressure itself doesn't depend on collisions, in the sense that you get the pressure is just a second moment of the distribution function. Okay, that's a different issue. Whether it behaves like a fluid, that is, you can well, no, I would say yes. However, it's usually a tensor. It's usually a tensor. If you can't isotropize the distribution function, then you have a pressure tensor, which actually you have in.
Atmosphere and the ionosphere, I think that deal with then fluid, so you can apply that kinetic theory.
Yeah.
In the fact that it's fluid, so you have the concept of temperature, the concept of pressure, gas, all of those things.
Of all the things, no matter whether it's a fluid or not, you just have a collection of particles. Okay, you have a pressure. We should talk about this more over lunch. Okay, so now I just gave you a very quick rundown of what we expect to happen in the case where the solar wind encounters one of our unmagnetized bodies. That because it has a neutral atmosphere, I didn't talk about the moon. It doesn't even have an atmosphere. That's interesting, but we're not going to talk about the interaction of the solar wind with the moon. But when it hits a body with an ionosphere, it sees a conducting ball, and it forms a bow shock and a sheath region around that ball. when it hits one of the magnetized planets, Earth, Jupiter, Saturn, etc., actually it's the magnetic field that, as we said, is generated by the dynamo of the Earth, or yeah, I'm going to mostly say Earth. If you really prefer to work with Jupiter, substitute the word Jupiter. Just basically our planet has a magnetic field, and the solar wind, which is a conducting plasma, interacts with that magnetic field first. Now, the first thing that you can notice is, well, this region that has a magnetic field from the Earth is going to present an obstacle to the solar wind the same way our sphere did. It's just more of a squishy obstacle, right? It's not a solid ball, but it's basically something where the magnetic field of the Earth is going to create this little region that the solar wind has to avoid. Same problem, though. It's a supersonic wind hitting an obstacle. It creates a bow shock, and it creates a sheath. Exactly the same analysis. That sheath, in the simplified analysis I gave you, is 18% as wide as this magnetopause distance here. That's called the magnetopause. But it's not a solid ball, so where does that pressure come from? We worked out the pressure over here. The pressure over here was basically 4/5 of the ram pressure. That's how much pressure is built up at the nose by taking the inflowing kinetic energy, converting it to heat here a little bit, and then a little bit more here. We got that 4/5. That pressure is on the outside, and I am going to take the very bold assumption of ignoring the magnetic field pressure of the solar wind entirely. I also ignored this magnetic field pressure when I did that other problem. But the magnetic field pressure from the Earth is pretty much all there is. Okay, so we have this Earth's magnetic field, and I'm going to go back to my potential magnetic field assumption. The assumption that the magnetic field around the Earth is curl-free. Not a perfect assumption, but it has gotten us a lot of mileage, and it'll get us a lot more. And so I have to solve Laplace's equation inside here. We do it with spherical harmonics. Here I'm only keeping the L equals 1, the dipole harmonic, and it has the decaying piece that goes as 1 over r squared. That is actually the part that comes from the dynamo. We talked about that yesterday. So I have a potential and therefore a magnetic field that goes as 1 over r cubed. That's the dipole magnetic field. But the magnetic field has to be confined inside this shell, so that can't be the whole story. We actually have to have the increasing piece as well. When we did this for the magnetic field of the sun, our boundary condition was that the magnetic field of the sun had to be radially outward at this artificial outer boundary. Here at this boundary, the magnetic field has to be tangential, not normal. So instead of a Dirichlet condition, I have a Neumann condition. And here I've solved Laplace's equation with a Neumann condition. I get a second term, which is due to the image, if you will, of the dipole. This is the solution for a magnetic field from a dipole that's confined. Actually, let's be honest, I did this confined inside a spherical shell. The radius of that shell I don't yet know. That is the radius of the magnetopause. But that is the magnetic field. Here's the magnetic field pressure. I basically take the gradient of this, square it. No surprise, I get something that goes as the Earth's radius to the 6th power, the magnetopause radius to the 6th power in the denominator, right? So I take the gradient, I get 1 over r cubed, and I square them, and I get 1 over r to the 6th. So far, so good. This is the magnetic pressure just inside here. The pressure balance, then, is that this magnetic pressure on the inside must balance the pressure that's built up in the magnetosheath due to converting ram pressure to real plasma pressure. When I put in that balance, I find that the magnetopause distance from there out to there should go as the magnetic field strength of the Earth and then divided by the ram pressure of the solar wind to the 1/6 power. Very interesting relationship here in Earth radii. Okay? If I put in some numbers here, that's about 12 Earth radii. This is for a solar wind speed of 400 kilometers per second. We saw that that's a pretty typical solar wind speed. And a solar wind density of about 10 to the minus 23 grams per cubic centimeter. Very low density. We're very far away from the sun. Okay, so I get about 12 Earth radii. Now I want to take a little quick break here for some intuition. The satellites, we have a bunch of satellites that are geostationary. SDO is one, the GOES satellites are another. More importantly, our satellite TV satellites are in geostationary orbit. How many Earth radii are they orbiting at? I had this number over dinner last night. 6. 6.5, right. If you don't remember it, one thing you could remember is that at low Earth orbit, if you're just going a couple hundred kilometers above the surface of the Earth, you orbit once every hour and a half, roughly. Then you have to remember Kepler's third law. Sorry, geostationary, you're going to orbit 1 in 24 hours. Kepler's third law is that that ratio of radii is the ratio of periods to the 2/3 power. Okay? So 24 over an hour and a half, 24 hours over an hour and a half, raised to the 2/3 power. Okay, I will admit it's challenging to raise this number here to the power 2/3, but when you do, you get 6.5. So our standoff distance to the magnetopause is 12 Earth radii. Our satellite TV satellites are safely inside the magnetosphere. Thanks to Nick's lab yesterday, we saw that that doesn't always help. What has caused in that event? Why was it that the magnetopause moved so far in, right? So that this calculation, I will claim this calculation still applies, but one of our conditions, it's this calculation here, has changed that brought the magnetosphere into 6 Earth radii and left the GOES geostationary satellites outside the protection of the magnetosphere. What had changed here? The magnetic pressure, right, which I've ignored, did come into play. The solar wind had a bigger magnetic pressure. Also had a bigger density, and I think a bigger velocity. So 2 things went into the denominator there. The Earth's magnetic field didn't change. That was not what happened. But the ram pressure here, and then I totally ignored the magnetic pressure. That basically shrunk the magnetosphere in. This balance shows you that that will happen. When this ram pressure goes up, the magnetosphere gets smaller, etc. How about the moon? Anyone remember this is an even harder number to raise to the 2/3 power. Remember the distance in Earth radii to the moon? How high the moon? What? I think it's close. That's astrophysically right, 40. Actually, if you take 28 days, 24 hours, you have to raise that ratio. I get about 58, 60, okay? But well outside of that magnetopause, okay? So the moon is outside our magnetosphere, at least on the side we've just been talking about. And then let's skip that. Here, I gave you a very quick and dirty calculation of that, of how big that was and how this worked. Here are some of the state-of-the-art codes. Yeah, it's different. You get different answers if you really do this honestly, but I'd say to 0th order, in terms of gaining a basic understanding, the arguments we just went through aren't so bad, okay? Now, let's just quickly visit the other planets like Jupiter. Jupiter, same calculation would be done. The magnetic field strength of Jupiter is 15 times greater than the Earth at its equator. Okay, it's about 5 Gauss instead of 1/3 of a Gauss, 15 times. The solar wind, however, has fallen in density by 1 over r squared, 5 AU, factor of 25. So the Jovian magnetopause should be at 50 Jupiter radii. This is actually even a little smaller than what's observed. That is this huge number. It is much bigger than the sun. Right? The solar radius is 5 times smaller than this. So the Jupiter's magnetosphere is truly huge. mostly because the ram pressure of the solar wind is way down, and the magnetic field of Jupiter, because we showed that dynamo, it really has such a good dynamo that it generates a very strong magnetic field. All right, but, very important, that was basically assuming the magnetic field of the Earth was confined to a spherical shell. That is not the case. We have the solar wind coming in. Now I will not ignore the magnetic field. It brings in magnetic field lines. The Earth has its magnetic field lines. We have, and I think you're going to hear about extensively this afternoon, magnetic reconnection that breaks magnetic field lines from the sun and the Earth and forms these magnetic field lines that start at the Earth and go into the sun, or start at the solar wind, and start at the solar wind and go into the Earth. What we call, these are also called open magnetic field lines. Okay, so we generate these new magnetic field lines that are basically open to the solar wind. And then on the tail side, which we haven't talked about at all yet, we're getting to there, they have to reconnect back so that the Earth's whole magnetic field doesn't just open up. So I get reconnection on the day side and reconnection on the night side in what's known as the neutral sheet. Okay, I'm going to assume that this reconnection occurs at subrate phi dot. That is, a certain amount of flux in Maxwell's is converted from solar wind to open, or closed to open, at a rate phi dot, Maxwell's per second. And in equilibrium, the night side reconnects the flux at the same rate. So we preserve a certain amount of flux that's open. And that gets swept back into the tail. That gives us a certain amount, there we want to say it, a certain amount of flux in the tail that just is basically in the process. It's been reconnected once and it's waiting to be reconnected a second time. Does everyone see that? It's kind of a balance. It's like, again, I hate to keep using toilets as an analogy, but we're always familiar with them. We have the tank in the back. Water comes in and it goes back out. The tank holds a certain amount of water. And on average, it has that certain amount of water. And it's the amount of water it takes to balance the inflow and the outflow. The magnetotail is the toilet bowl tank of the magnetosphere. It is holding the magnetic flux that has been reconnected on the day side and is yet to be reconnected on the night side. And it's going to be reconnected in this long plasma sheet and then swept back into the Earth. The length of this is something we really can't work out with these simple calculations I've been doing. It is very, very long. The moon is at 60 Earth radii. It's out here. So well outside this magnetopause, but inside the magnetotail when it goes through. Okay, in this kind of cartoon picture. So in this magnetotail, the magnetic field lines from the night side are coming in here, going into the North Pole, going out from the South Pole, and just going way back down. And we have this place where the magnetic field is switching from outward to inward. It's a current sheet. Right? Use the right-hand rule. You have current coming straight out of the page all along this sheet. Okay. And we have the same story at all these other places. Neptune as well. The boundary between these open and closed field lines, basically it's all the field lines that have been reconnected to the solar wind and are open and are waiting to be closed back down. That's some angles worth of field lines. And the boundary between these, open and closed, is what forms the auroral oval. Beautiful picture here of the auroral oval. Here is North America. There's Alaska. You can see Russia from there. You've got, etc. There is the ring that defines all of the magnetic field. Here, all the magnetic field is open to the solar wind. You'll notice the aurora is not created by particles from the solar wind, right? There's no aurora there. If you went way up and you were on the Franklin expedition up there, you wouldn't have seen aurora overhead because you're just looking at field lines that are open. It's this interface that gives you the boundary. You can estimate how much this is if you assume that the amount of flux in the polar cap is the same as the amount of flux in the tail, okay? And you can work out what that is if you know the latitude of the polar cap. So say that that's 75 degrees latitude, so you have 15-degree angle there. Theta of polar cap is 15 degrees. Then you basically have 10 to the 17 Maxwells. Maxwell is a Gauss centimeter squared. That's the astronomer's unit of flux. If you assume that that magnetic flux is in some uniform pressure, uniform magnetic field B tail, and put it in pressure balance with the solar wind, you can work out that you have a radius of a tail of about 25 Earth radii. So although it's only 12 Earth radii from the Earth out to the magnetopause, and another 20%, 18% of that out to the bow shock, if you go up from here, you go about 25 solar radii, and we get about 10 to the minus 4 Gauss in the magnetotail. Okay? Some beautiful pictures of aurora on other planets. Same story. I'm going to leave it at that. Right? The reason we have the structure of the magnetosphere we do is because our planet has a dynamo, so does Jupiter, so does Saturn. The dynamo is encountered by the solar wind, just as it is in Jupiter and Saturn. So you have some nice auroral ovals. This one you can actually see a bit of the northern and southern caps. All right, the last subject. We have to talk about the interaction between the magnetosphere that's created by this whole process and the ionosphere. Okay? Now, we have the field lines here that are reconnected, and I'm going to assume that the magnetic field from the sun is going to the south. This is called the southward IMF. It reconnects at this rate we've talked about, phi dot, and then it's swept backwards. So the field lines are being moved by this conducting plasma. They're frozen to the plasma and they're moved to the tail, and this whole field line moves. But wait, the field lines are frozen into the solar wind, which is moving this way, but they're also frozen into the Earth's core. That was our lecture yesterday morning. And that is not moving. I mean, that is moving at, what did we say, 0.3 of a millimeter per second. This is moving at 400 kilometers per second. So I can't move the feet of these field lines because they're frozen into the core of the Earth. True? Is that a problem? It's true that they're frozen into the core of the Earth. It's true that they're frozen into the solar wind. So the two ends of the field line then have very different masters. One is stuck at the core and the other is moving with the solar wind. This is a bit of a appealing to those people who have looked a bit at frozen in fields in plasmas. Why is a field line real in a plasma? And it is real. It's made of stuff. All the stuff, which is plasma, is frozen to the field line. So the field line basically has all this stuff on it. It's made of stuff. That's what it means to be real. Ghosts are not real. They're not made of stuff. It also means things like honesty is not real because it's not made of stuff. Okay, I have a very physics view of reality. But a field line is a real thing because it's made of stuff. And if it's got two ends and and one of them's moving and the other isn't, I mean, it's going to get really yanked around. Does this bother anyone? Does anyone see a way out of this conundrum? So the field lines are real when you have a plasma or any sort of good conductor where stuff is frozen to them. And the stuff, the solar wind, is moving at 400 kilometers per second over here, and it's going to try to move all the field lines back towards the tail. At the core of the Earth, they're frozen to this iron molten goop that is also an extremely good conductor. Magnetic Reynolds number, if you remember, was, I think it was 100 or something. Good conductor. So they're frozen going 0.3 millimeters per second, not 400 kilometers per second. So what gives? The answer is there's a gap between the solar wind and the core, known as the Earth's atmosphere and the Earth's crust, where the conductivity is not high. The field lines are not frozen. In fact, at that point, field lines could be considered imaginary. And in some of your classes, your teachers may have told you that field lines are just imaginary and they're not real things. And you have to forgive these misguided souls who told you that, because they probably lived in this gap where the conductivity of the stuff around them was not so high. Right? They lived in the Earth's atmosphere, stood on the Earth's crust. Field lines there are imaginary, so we don't even have to think about field lines there. In the core of the Earth, we think about field lines. They get all wrapped up. That's what created our dynamo. In the solar wind, okay. So we really want to think of the Earth's atmosphere as this insulator, and all the field lines essentially end right there, or at the ionosphere. This is what happens when you have a layer with some resistivity here, the ionosphere, an atmosphere that's a perfect conductor, and a solar wind, sorry, that's a perfect insulator, and a solar wind that's a perfect conductor. I'm going to move the material in the solar wind to the right as sort of an upper boundary and watch these frozen-in field lines move with it. And I'm going to do this actually very sort of impulsively. I'm going to start with straight magnetic field lines. You see, I haven't drawn the field lines below here because they're imaginary below there. So I don't even really think about field lines. They essentially end. Now, I could trace field lines below this, and people will tell you field lines don't end. But I'd be tracing something that's imaginary, and that just, I don't like doing that. So I'm going to trace them where they're real, and they just basically end at the ionosphere. But the plasma moves to the right. The field lines get swept back. There's a layer of current that is just here where the field lines bend. You can use the right-hand rule. Field lines are bending. That creates current coming out of the page here. I've turned everything on its on the side. Field lines are coming out here. The current, right-hand rule, is going to the right. Now, I am not moving all, if you turn it on its side, I'm only moving a slab of plasma. So the field lines are only coming out within this region here. And so there's also current that has to come and basically enclose all of this. This is a thought experiment. It's not a simple thought experiment, but it doesn't have all that many pieces to it. Does everyone see what's going on here? I have flow to the right in the red arrows. It's sweeping the field lines back because this is the MHD magnetosphere, therefore creating a magnetic field that goes to the left, a current that comes out of the page, and minus V cross B, that is the electric field I see in the lab frame, is actually also out of the page here. But the electric field is everywhere above this current layer. The electric field and the current are not really related. Okay? The electric field comes from V cross B. The current comes from curl of B. Those two things have nothing to do with each other. Well, they have B in them, okay. But, right? Does everyone see? This is where things get very, very confused among our two communities. Confused is a polite word for it, okay? Tim can probably back me up, or Amitava, that the two communities have great, the people who study the ionosphere and the magnetosphere have difficulties right here. But I'm going to talk us through this. And the velocity does this. Okay. A little while later, that current layer has moved down. Basically, this layer of bending has moved down because the solar wind is acting. Now, finally, we get to this point here. The current layer, where the fields are bent, have moved all the way to the base. And it can't move any further because I no longer have an MHD plasma here. The current is now inside the ionosphere. Okay? At least this portion of the current is inside the ionosphere. The ionosphere is a resistor. Okay? So in the ionosphere, the electric field and the current are related. And it's basically E is J over sigma. So the electric field that here was created by V cross B, in the ionosphere, I can think of it as just being created by the current itself. And the current, which was created by the curl of B here, is still created by the curl of B. Okay? So I have current through the ionosphere. I have current through the magnetosphere. that all came about for the same reason, curl of B, because I only moved one slab of material forward. So I have currents going down, coming across, and going back up again. Everyone see this pattern? Very simple thought experiment. The electric field in the atmosphere is basically the same as it is everywhere else. Why? It's a perfect insulator. It doesn't care about an electric field. Who cares? It doesn't care about a magnetic field. Okay, so we have the electric field everywhere now. It's basically uniform. It has different characters. Here it is V cross B. I still have velocity moving to the right. I still have velocity going into the page here. That's creating the electric field up here. Okay, and then we see that what really appears to be happening, because I refuse to draw the field lines below the ionosphere where they're not real, is it looks like the ends of the field line are just moving across the ionosphere, being swept by the solar wind. And they stop there because below that, they're not real. Okay? So we get this field line motion, and it relates to an electric field, which I can think of as creating the current in the ionosphere. Okay? Then I have these other currents that basically have to completely surround the slab of flux that I've moved. And this is what creates what's known as the polar cap potential. I have my field lines being swept back, going from position 1, 2, 3, 4, 5, 6, 7, 8, then all the way back around 9. Because after all, I have to get the field from the tail back out to the bow, to the day side, from the night side to the day side, so that it can be reconnected again. And if I watch those foot points move, and here we're looking at the north pole of the Earth, the polar cap, the foot points, which are being just moved along the ionosphere, where they stop being real, goes from point 1, 2, 3, 4, 5, 6, 7, 8, 9, forms this little swirly thing here, which through some great feat of imagination, someone referred to as convection. It has nothing to do with thermal convection. It is just a motion around in a circle. But this is called the convective flow. And I can take the electric field, which we argued is just coming from V cross B up here, but basically being put into the ionosphere as the same electric field, and I can integrate it from point A to point B. That gives me something known as the polar cap potential. That has to match, if you followed this whole argument, the rate of magnetic reconnection on the day side. The rate at which field lines are being supplied over here, basically they all have to pass through some line that connects A to B. So if I integrate that electric field, I get the polar cap potential. And so this is the version from the textbook. We have, this is a view. Here's the day side. There's the night side. Here is the convective flow. The foot points are moving from day side to night side, then sweeping back around. As you can tell, it's hand-drawn. This is A to B. I integrate the polar cap potential. There's also these currents here. These are the Birkeland currents. These are the parts that go along the magnetic field in the field aligned in the MHD region. So they come out of one side. What would this be? This would be the dawn side. They go into the dawn side and come out of the dusk side. Simple picture. And you can put in the numbers. Polar cap potentials are typically observed to be about 50 kilovolts. I think in your lab yesterday you saw some plots of polar cap potentials. They kind of looked like this in at least one hemisphere. So 50 kilovolts, if you turn this into Webers per second and then multiply by 10 to the 8, you get 10 to the 12 Maxwells per second. We argued based on the size of the auroral oval that we had 10 to the 17 Maxwells in the whole polar cap. So this basically means our toilet bowl tank is being replenished every 5 hours. I have flux going in at a rate of 10 to the 12 Maxwells per second, basically being stored in the magnetotail and then being flushed out through the night side at the same rate. So each one lasts about 5 hours. Again, that's an average. All right, that is it for the solar physicist's view of the ionosphere. Sorry, we're not really actually over time because we started so late. The whole ionosphere is created by EUV and X-ray photons. It's diminished during the nighttime, but doesn't go away because essentially you need to recombine it with ions, and then the sun rises the following day and replenishes it. The solar wind is deflected by the ionosphere, which is a conducting boundary, if there's no magnetic field, like on Venus and Mars. Otherwise, it's deflected by the magnetic field, the magnetosphere, and the magnetosphere tail is created by this process of reconnection. Day side moved back to the night side and then swept back in. All right, that is the overview. Any questions on anything from the last 4.5 hours of lectures? Anything in our solar system that I discussed? Yeah. That's a good question. It puzzled me for a long time. In this simple model, what I've done is taken this. So here are a whole bunch of field lines. Do you see this? And they're all going straight down. And I am taking only a section of them, outlined here in orange, and moving them towards you. Sorry, moving them back, away. So I'm sweeping them back, but only those. So that creates a magnetic field out of the component, out of the page here. That's why they're going to the left here, okay? But there's none here. Now apply the right-hand rule right here. I have magnetic field out here, no magnetic field there, and I get downward current. There's this layer of current that separates field that has been slanted from field that is just as it used to be, standing straight up. No component into the page or out of the page. Okay? That's the source of that. It's basically the boundary between field lines that's being moved and field lines that's standing straight up. Moved, standing straight up, I've got a discontinuity in the direction of the magnetic field. I have a curl, a magnetic field. Why are they field aligned? Well, what you have to do is picture that actually the field reverses across them. But if you pick an angle that's in the middle, the current is going in that direction. There's an average magnetic field that goes in that direction, and then a component that completely cancels. It's a very subtle trick of sums and differences. But it's created by the difference between field that's moved and field that isn't moved. Those are field-aligned currents. Yeah. Oh, yeah, sorry, I thought I mentioned that. This is the same thing as that, but viewed from over here. This is the view from over here. Okay, so if I look at these arrows here, they're going away from me. That's the little cross. If I look at these arrows here, they're going down and towards me, down and towards me. And here I can't see that there's some stuff in front of me that I'm not moving and stuff behind that I'm not moving. But in the slab view, you see that some is moving, some is staying straight up. Sorry, some of these diagrams take me like 2 days to produce, and then I throw them at you so quickly that you can't digest them. It takes me 2 days to make them. Any other questions? Yeah. The polar cap potential? Yeah. So I would answer, I don't know, this is not something I know from an observational standpoint. But I would turn your question around and say, well, so point out that the rate at which it's reconnected here is roughly the same as the rate at which it's moved backwards. And that is so there's the rate of flux transfer. This is the polar cap potential, A to B. So my understanding is somehow, and I can't tell you how they do this, they can measure the potential in the ionosphere. I will also point out that that electric field that's in the ionosphere is also present below the ionosphere. So naively, one could say, I could just measure this from the ground. It's not that easy, but the electric field that's due to the reconnection is imprinted on the ionosphere and will be present below the ionosphere. So that's one way you would do it. Specific, I'm sorry. Tim, do you know how they measure polar cap potential? I see it come out of super darn. That doesn't mean anything to me. Yeah, what kind of instrument? Yeah, he's asking about which instruments do it. Okay, yeah, so, yeah. Yeah. I didn't, yeah, I did not go through all that details. We could talk about that. I could talk about that for hours. The actual mechanisms from the solar corona where we get X-ray and EUV emission. We should, there's a huge amount of interest in that specific topic. I love it, but. Or we could go upstairs and talk to Phil Judge, and he could talk to you for literally years about that. Anyone else? Questions that might be slightly easier to answer. Okay, let's take a break and we'll get back here. I'm afraid it's only 15 minutes, but